Welcome everyone. In this lesson, we will explore the architecture and function of neural networks, focusing specifically on how they are used for classification tasks. Neural network classification is a powerful technique that allows us to build models that can categorize data, solving problems that come up in fields like image recognition and natural language processing. Our journey today will begin with the fundamental building blocks of a neural network. We will then examine how these networks learn by adjusting their internal parameters through a process of trial and error. To make these concepts tangible, we will walk through the process of building a simple neural network from the ground up using Python. Our main learning objective is to demystify how these complex systems operate, giving you a clear understanding of how a network takes in data, processes it, and ultimately makes an intelligent decision. By the end, you will see how the pieces fit together to create a functional classifier. Let us break down the basic architecture of a neural network into its three primary components. First is the input layer, which is the entry point for our data. Each node in this layer represents a single feature of our input. For example, if we were analyzing an image, each pixel could be a feature fed into an input node. Next are the hidden layers, which are the computational core of the network. These layers contain neurons that perform mathematical transformations on the data they receive from the previous layer. They use special functions called activation functions to introduce nonlinearity, which is what allows the network to learn and represent complex patterns. Finally, we have the output layer. This layer produces the final result. For a classification task, the nodes in the output layer typically represent the different classes we are trying to predict, giving us the model's final answer. Within the network, every connection between nodes has a weight, and each node itself has a bias. These weights and biases are the parameters that the network tunes during the learning process. The output from any given node is determined by applying an activation function to the weighted sum of its inputs plus its bias. Activation functions are essential because they introduce the nonlinearity that enables neural networks to solve complex, nonlinear problems. Without them, the network would just be a simple linear model. We have several types of activation functions. The sigmoid function outputs values between 0 and 1, which is very useful for binary classification. The rectified linear unit, or ReLU, is computationally efficient and outputs the input if it is positive and 0 otherwise. The hyperbolic tangent, or tan function, is similar to sigmoid, but outputs values between -1 and 1. Lastly, the softmax function is ideal for multi-class classification, as it converts the output layer's values into a set of probabilities that all sum up to 1. The process of training a neural network involves two key steps that are repeated iteratively: the forward pass and the backward pass. During the forward pass, input data is fed into the network and flows through the layers from input to output. At each layer, the weights, biases, and activation functions are applied to transform the data until a final prediction is made. The backward pass, also known as backpropagation, is where the learning actually occurs. The network compares its prediction to the true label and calculates an error. It then propagates this error backward through the network, using calculus to determine how much each weight and bias contributed to the error. This information is used to update the parameters, making small adjustments to improve the network's accuracy. This entire cycle of forward and backward passes is what we call training, and it is repeated many times until the network learns to make accurate predictions. To make these ideas more concrete, let us consider a practical example. Imagine we want to build a neural network that can classify handwritten digits. Our input would be images of these digits, where each image is composed of a grid of pixels, say 28 by 28, which gives us 784 individual input features. These features are fed into a 3-layer neural network. The network's job is to process these pixel values and decide which of the 10 possible classes, representing the digits from 0 to 9, the image belongs to. This example helps us visualize how a complex, high-dimensional input can be systematically processed through the network's layers to produce a simple and meaningful categorical output. To train a network, we need a way to measure its performance. And this is where the loss function comes in. For classification problems, the most common choice is the cross-entropy loss. This function quantifies the difference between the model's predicted probabilities and the actual true labels. In binary classification, the loss L is calculated as the negative average of the sum of two terms, the true label times the log of the predicted probability, plus 1 minus the true label times the log of 1 minus the predicted probability. This formula heavily penalizes predictions that are both confident and incorrect. A similar formula exists for multi-class classification, where the loss is summed over all possible classes. The ultimate goal of training is to find the optimal weights and biases that minimize this cross-entropy loss, making our model as accurate as possible. The most traditional method for training neural networks is an algorithm called backpropagation. At its core, backpropagation is a clever and efficient way to compute the gradients of the loss function with respect to every weight and bias in the network. It does this by applying the chain rule of calculus, working backward from the output layer to the input layer. Once these gradients are calculated, they tell us the direction of the steepest increase in the loss. We then use an optimization algorithm, like gradient descent, to update the network's parameters by taking a small step in the opposite direction of the gradient. While backpropagation is highly effective, it is important to remember that it is a local optimization technique, which means it can sometimes get trapped in local minima or saddle points, rather than finding the absolute best solution. Now, let us transition from theory to practice with a hands-on example. We are going to build and train a simple neural network that has one hidden layer. The task for our network will be to classify data points into one of two distinct classes, which is known as binary classification. To keep things clear and understandable, we will work with a synthetic dataset that we create ourselves. This approach allows us to see every step of the process, from defining the network structure to training it with backpropagation, and finally evaluating its performance on the classification task. We start by preparing our Python environment. The first step is to import the NumPy library, which is fundamental for numerical operations and is especially powerful for handling the matrix multiplications that are central to how neural networks work. Next, we define our activation function, which in this case is the sigmoid function. This function is responsible for squashing the output of a neuron to a value between 0 and 1, making it ideal for representing a probability. We also create a function for the sigmoid's derivative. This derivative is essential for the backpropagation algorithm, as it helps us calculate the gradients needed to update our network's weights during training. Here, we implement the cross-entropy loss function that we discussed earlier. This Python function takes two arguments: the true labels from our dataset and the predicted probabilities generated by our model. It then calculates the cross-entropy loss, which serves as our measure of error. A smaller loss value signifies that the model's predictions are closer to the true labels, indicating better performance. The main objective during the training phase will be to systematically adjust the network's parameters to minimize the value returned by this function. To train our network, we need data. In this step, we generate a simple synthetic dataset. We create a set of 200 data points, where each point has two features drawn from a standard normal distribution. We then assign a binary label, either 0 or 1, to each point based on a specific rule. The label is 1 if the product of the two features is positive, and 0 otherwise. This method creates a dataset with a clear, non-linear boundary between the two classes, providing a suitable challenge for our neural network to learn and classify correctly. Now we initialize the parameters that define our neural network's architecture and training process. We specify that our input layer has two nodes, corresponding to the two features in our data. The hidden layer will have 4 nodes, and the output layer will have a single node to produce the binary prediction. We initialize the weights connecting these layers with small random values and set the biases to 0. We also define our learning rate, alpha, which controls the size of the steps we take during gradient descent. Finally, we set the number of epochs, or training iterations, to 10,000, which determines how many times the network will see the entire dataset. Let us review the structure of the network we have just set up. The input layer consists of 2 nodes to handle our 2 input features. These inputs are fed into a hidden layer of 4 nodes, with the connections defined by the weights W1 and biases B1. A sigmoid activation function is then applied. The output from this hidden layer is passed to a single output node, with its connections determined by weights W2 and bias B2. Another sigmoid function at the output node produces our final probability. The training itself is governed by 2 key parameters: a learning rate of 0.01 and 10,000 epochs, which together guide how the network adjusts its weights and biases to learn from the data. This code block contains the training loop, which is where the network actually learns. For each of the 10,000 epochs, we perform a series of steps. First, in the forward pass, we push our data through the network to generate predictions. Then, we compute the cross-entropy loss to measure the error. The backward pass follows, where we calculate the gradients for all the weights and biases, determining how each parameter contributed to the error. Using these gradients, we update the parameters with gradient descent, making small adjustments to improve the model's accuracy. We also print the loss every 1,000 epochs to monitor our training progress. Finally, we plot a learning curve to visualize how the loss decreases over time, confirming that our network is indeed learning. Once the training is finished, our network's weights and biases are optimized, and we can use it to make predictions on new data. We create a separate, independent test dataset using the same method as before. We then feed this test data through the trained model in a forward pass. The model's output is a probability, which we convert to a binary class label by applying a threshold of 0.5. If the probability is above this value, we predict class 1, otherwise we predict class 0. To evaluate how well our model performs, we calculate metrics like accuracy and precision and generate a confusion matrix. This matrix gives us a detailed breakdown of the model's correct and incorrect predictions for each class. In this session, we have covered the essential concepts of a neural network for binary classification. We started by understanding its basic architecture, including the roles of input, hidden, and output layers, as well as the importance of weights and biases. We explored how activation functions introduce nonlinearity, and how the learning process is driven by the forward and backward passes of backpropagation. By building a simple network from scratch, we saw how to initialize its parameters, train it using gradient descent to minimize cross-entropy loss, and finally, evaluate its performance. This lesson provides a solid foundation for understanding how neural networks learn and for building more sophisticated models in the future.